Section 1:1 Introduction to Statistics. When we talk about statistics, we are talking about numbers, and numbers can be looked at within two unique ways. There's data, that's information of counting, measuring, observing, and then there's statistics. This is organizing our data to try to make sense of what we're looking at, to look at order within it. Statistics gives us translation of what we're observing. We use rules and methodologies to determine if these patterns make sense, if we can make further judgment of these patterns, and if these patterns are an accurate representation of what's going on. Within statistics, we have populations, we have samples. The population is the entire group. A sample is a part of that group. Don't mistake the term population for, let's say, the population of the United States, which is a population. I can talk about the population of a classroom. In our classroom, we have 28 individuals. That's the population as I've defined it. If I take a sample of our classroom from those 20 individuals, that would be 7, for example. 7 individuals as a representation of the population of the 28 individuals. That's 25% of my classroom population. How do I find it? Simply by having the 7, the sample, in the numerator, and then the population, the 28, in the denominator. Now, the population of the state of Georgia is 10.62 million people. If I do a sample, and there's many different ways of doing samples, we can look at other ways we should sample, and we're going to talk about that next week. But right now, I'm going to do what's called a stratified sample. And I want to be consistent with it. Don't worry about the terminology. I'm just giving you, no pun intended, the example here. There's 152 counties in the state of Georgia. More counties in Georgia than any other state, by the way. I'm going to take 10 individuals from each county as my sample. So 10 individuals from each county times all 152 counties means there's 1,520 individuals. The sample of 1,520 individuals, when I divide it by the entire population of Georgia, that's 0.014313%. Now, is that a valid sample? Is that a good sample? Is it an accurate sample? We're going to talk about these all semester. But what we did is we took a sample from the entire population. And we're also going to learn what kind of inferences, what kind of judgments can we make from these samples in reference to the entire population. Now, actually, we do sometimes survey entire populations. The United States, within our Constitution, actually is required to take a sample every 10 years. Our founding fathers put that within there. And anytime you talk to the entire population, whatever that entire population is, it actually is called a census. However, the problem is censuses take a lot of time. We do it every 10 years because there are 330 million people now in the United States. That takes a lot of time to just get not only the information out, but get it back and categorized. If I did a census of Berry College, I would talk and get data from all 1,800 students at Berry College. Now, there's parameters and statistics as well. The parameter is for the entire population of what we're observing. The statistic is for the sample of the population. A parameter. For example, a parameter is the entire population. In this case, 10 U.S. senators vote for a measure. I know within our U.S. Congress there's only 100 senators. So 10% of the U.S. senators voted for it. That means only 10 would, because I know the population of the Senate. 40% of 1,211 students at a particular elementary school got below a 3 on a standardized test. There's a parameter because I already mentioned right in that first sentence how many students are at the elementary school, 1,211. 33% of 120 workers at a particular bike factory paid less than $20,000 a year. Well, I have all 120 workers listed, so I know if it's 33%, which would be 40, then I know that's a parameter. It's not a representation, it's not a sample, it's the entire population we're looking at here. Good to remember this is parameter, starts with the letter P, and so does population. Statistics is where we have a sample. 60% of US residents agree with the latest healthcare proposal. I do not think all 330 million people in the United States were contacted about a healthcare proposal. They probably took a sample and projected that for the entire population. 45% of Jacksonville, Florida residents reported they've been to at least one Jaguars game. The population of Jacksonville, Florida, and the metropolitan area is 1 million people. I do not think we had the time or capability to sample all 1 million people for a relatively, random and not that important a question. So they probably took a small amount. And I know that's a statistic. 30% of dog owners poop scoop after their dog. I read somewhere 250 million pet owners. Well, let's assume half of them own dogs. I don't think they sampled 100 million people in the United States to see if they poop scoop their dog. So we are going to make an assumption here. These are statistics where they project it on the entire population. Now, like parameter, we start with the letter P and P for population. Statistics starts with the letter S, as does sample. Descriptive statistics. There are two types of statistics we can talk about: descriptive statistics and inferential statistics. Descriptive statistics is literally just what it sounds like. We're describing the characteristics of a data set. Often we do this so we can observe it much more readily, like with a graph or a table. It's easier to see when we set it up in a certain way rather than looking at the raw data itself. But again, we're observing, we're describing, we're not making conclusions from this. It allows us to see what is going on, but we cannot interpret this unless we have more meaningful data behind it or methodology, which we'll be talking about this semester. Here's an example of a descriptive statistic. We've sampled 14 people here, got their age, got their gender, got their car color. Well, one set of data says looks like we sampled, how many men? 25 males and 15 females. So actually, the data set's larger than what we're showing here. And I would say I'm not sure this is a really good set of data because I know within the United States, our population percentage of male to female is roughly 50-50, 50% male, 50% female. So I'm not sure this is accurate, but we're not talking about that yet. We're just observing here, and that's important itself. We can observe this may not be a very robust sample just because of the males almost having twice as many as females that were sampled here. The other area we're looking at is the color of cars that they like. Number one, I'm just observing this, 24% is white, 22% they like the black color, 19% silver color. This is important because if I was a paint company or a car company, I'm going to want to know how much paint to make or how much paint to buy. And I'm not going to buy the same amount of red as I am white based on this past data. That's the kind of stuff we can observe. Red only has 10% compared to 24% for white. White is 2.5 times as big. Red is only half of what black color is. So when I look at this, I can make some good, steady observations here. Is it representation? I don't know yet because there's twice as many males as there are females in this raw data. So I'm not comfortable. But I'm making a description here. And what's interesting is With descriptive statistics, we can also look at, is it a valid data set? And this, that male to female population range, descriptive statistics says, I'm going to question that. I need to look further. Here's another example of descriptive statistics. This shows the average weekly earnings based on education, as well as those education levels, what their unemployment rates are. People who have less than a high school diploma, they make an average of $493 a week, and they have an average of 8% unemployment rate. A doctoral degree has an average of $1,623 per week and an unemployment rate of 1.7%. Now, we're describing this. We're just looking at this. I can't make inferences from this. I can't make judgments. And notably, for one reason, I don't know what the populations are here. I've just got some information. And this is the thing with statistics you have to be careful about. And I talk about this, especially when you're looking at the media. I don't know if there are more people with doctorate degrees or more people with less high school diplomas. And because of that, I cannot make a judgment or assumption here. This looks like the more better educated you are, the more money you'll make. But what's the demand for these master's, professional, doctoral degrees compared to less than high school diploma? And then the unemployment rate also. I don't know how many people are unemployed in the grand scheme of things. I've just got percentages here, and we have to be careful with this because we're not getting the full picture. We're describing some data here, and it's some pretty interesting data. But I don't know the entire story because we don't have the raw data where this was built from. And this is where you're going to have to be careful when observing things, especially as you become out into this world and learn more and more. You're going to question things like this. How many samples are there? How big is the sample? How was it attained? These questions are what you need to ask when you're looking at data. Overall, there's two of the most common types of descriptive statistics. We'll talk about this next week. Measures of central tendency. That is the mean, median, and mode. The mean is another way of saying the average. I've got 9 numbers here: 2, 4, 6, another 6, 7, 8, 11, 13, 14. The mean is all those numbers added up divided by the number of numbers there, which is 9. If I add 2, 4, 6 plus 6 plus 7 plus 8 plus 11 plus 13 plus 14, I get 71. If I add up by 9, that's the number of numbers there, I get 7.89. So the mean, or the average, is 7.89. The median is the middle number. It's this number right here. Right there. And I know it's the middle number because there's 4 on this side and there's 4 numbers on this side. It's the middle number. And then the mode is the most common number. There's only 1, 2, there's 2 4s. There are, I say 2 4s? 1, 2, 1, 4, 2 6s. 1, 7, 1, 8, 1, 11, 1, 13, 1, 14. So it is these 2 6s. There's 2 of these here. So that's the mode, the most common number. And then measures of dispersion, to disperse, the spread, the variation. Range is one of the best examples here. And what is the range? It's the difference from the highest to the lowest. My highest being 14 here, and my lowest being 2 here. And I find the difference. 14 minus 2 is 12. So my range is 12. This is one type of descriptive statistics we look at. And these are within 2 areas: measures of central tendency and measures of dispersion. By the way, we'll study this more next week, but the reason we call them central tendencies, if you look at our mean, 7.89, our median 7, and our mode is 6, they're all around this area here, right in the middle, central Tennessee, the center part of all this. Inferential statistics is the other type of statistics. This is where we make a judgment or we make a guess or what we usually call it a hypothesis to see if that sample is representative of the entire population. We're going to take a small group and make an assumption that small group from the large population is representative of all of it. Simple inference would be I sampled 25 people within the cafeteria at Berry, and 20 of them like Doritos. That's 80%. So I'm going to make an assumption with that 80% of the Berry campus like Doritos. Pretty simple example. I'm not sure how accurate it would be, but that is an inference. We're taking an observation of a sample and then projecting that onto the entire population. And that's what we're really going to learn, especially in the second half of statistics. How accurate is that? What levels of accuracy can we look at? How do we know how much variation there is within that? Now, I worked in the healthcare industry for 28 years as a market analyst. So I'm going to present a lot of health data to you because there's a lot of health information available, millions and millions of people, and there's a lot of different sorts of data we can look at readily and graphically. Now, again, with the inferential statistics, we take a sample out of the entire population. As you can see here in this pie chart here, that sample is part of the population. It's a piece of it. And I've got here is some actual data from the U.S. Health and Human Services. The limitation of activity caused by chronic health conditions. Limitation of activity as people get older, they have ADLs, activities of daily living limitations. Being able to get up in the morning, getting dressed on your own, being able to feed yourself. And there are chronic health conditions which can affect a lot of these. For example, arthritis does literally make it difficult to get up, heart problems, diabetes, lung conditions, vision conditions, hearing problems, and then even dementia. As you can see here, we've got some interesting data. From ages 65 to 74, we've got less people with these health conditions than we have 75 to 84 across almost all different health condition types. And then 85 and over have the greatest amount. So I'm going to make an inference here, looking at this, that the older the person is, the more likely they're going to have chronic health conditions. They didn't check all the information here. In fact, you can see these numbers here. From 65 to 74, that blue, which is arthritis or other musculoskeletal disorders, 122 people. 96 people have heart or other circulatory problems from the ages 65 to 74. 75 to 84, 167 have arthritis conditions, 138, more than the 65 to 74 for those same health conditions. And you see it greatly increases in the 85 and over. 281 have arthritis, and 204 have health conditions. Now, I'm going to assume it's the same population. It says per thousand, so that's interesting. It's out of 1,000 people. 122 out of 1,000 are between the age of 65 and 74 have arthritis conditions. So by looking at this, we're going to infer that this sample is representative of the entire population. And that why the sample shows this, we're going to make an inference that all people 85 and over, on average 281 out of 1,000, or 28.1%, will have arthritis conditions. 20.4%, or 204 out of 1,000, will be 85 and over and have heart conditions. We do this just like we were doing before. We're looking at the car colors. Is that a hospital needs to set up how many people are going to be visiting for various things? What kind of medication should we have on hand? What should the pharmacies have available for these people? How much should we produce, the manufacturers? Because, and I ask you this because drugs, just like food, go bad after a while. You don't want to make so much that it goes bad and has to be recalled. You want to make enough to supply the population. And that's just one example of where we use inferential statistics. And we're going to talk about this semester how accurate this will be, or what's the range of accuracy. Now, when we overall talk about descriptive statistics versus inferential statistics, within descriptive statistics, we're concerned about describing the target population, which is the description. Inferential, we're making an inference, we're making a judgment, and we're assuming what we see in the sample is representative of the population. Descriptive statistics simply organize and analyze the data. It takes it from raw data and actually puts it in categories. Inferential statistics uses it to compare things, to predict things, to make assumptions with it. Final results are shown in graphs, tables, charts with descriptive statistics. We're going to do bell curves and probability scores. Those of you who had statistics in high school probably recognize this, but I will teach you how to do this. It's not difficult. We already know the data, which is already known within descriptive statistics. We are looking at 25 cars or 5,000 people. But with inferential statistics, we're taking a sample and projecting that as a relation to the entire population. Finally, with descriptive statistics, we're looking at what I talked about, some measures of central tendency, the mean, median, mode, the range. We're going to talk about standard deviation. And these are just observations. We're not making a judgment on them. But with inferential statistics, we're going to do tests. We're going to make an assumption based on the sample and project that for the population to a certain level of accuracy.